Hello everybody, this is the 5th day of our crash course, and we're going to learn LLM evaluation and optimization techniques. The evaluation and optimization of large language models, LLMs, is crucial for determining how well these models perform across a variety of tasks. Unlike traditional models, LLMs exhibit complex behaviors and can serve many applications, including text generation, translation, and question answering. Therefore, evaluating their performance requires a holistic approach that considers both quantitative metrics and qualitative insights. Optimization techniques, on the other hand, focus on improving efficiency, reducing computational requirements, and enhancing the quality of predictions. This lecture will introduce key metrics for evaluating LLMs, including task-specific performance measures, as well as a range of optimization strategies aimed at making models more efficient and accurate. When evaluating LLMs, several performance metrics are commonly used depending on the task at hand. For classification tasks, accuracy, precision, recall, and F1 score are standard metrics that give insight into the model's effectiveness. Perplexity is often used for language models, indicating how well the model predicts the next word in a sequence. A lower perplexity suggests a better model. For text generation tasks like machine translation or summarization, metrics such as BLEU, bilingual evaluation understudy, and ROUGE, recall-oriented understudy for gisting evaluation, scores are used to compare generated output to reference outputs. Additionally, tasks like named entity recognition, NER, have specialized evaluation metrics like entity-level precision, recall, and F1 scores, tailored to assess how accurately the model identifies and categorizes entities in text. While automated metrics are useful for initial assessments, human evaluation remains vital for assessing more subjective aspects of LLM outputs, such as fluency, coherence, and relevance. Human evaluators can provide insights into how natural and contextually appropriate a model's responses are, which can be especially important for tasks like dialogue systems or creative text generation. However, human evaluation is time-consuming, expensive, and inherently subjective. Evaluators may disagree on how to rate certain qualities of text, leading to inconsistencies in evaluations. A hybrid approach, combining automated metrics and human feedback, often produces more reliable results by leveraging the strengths of both methods. Generalization is the ability of a model to perform well on data that it hasn't seen during training. For LLMs, evaluating generalization involves testing the model on diverse datasets and out-of-domain examples to ensure that it doesn't overfit to its training data. Evaluating robustness is another key aspect of LLM performance. This refers to the model's ability to handle noisy or adversarial inputs without failing. Adversarial testing involves crafting input sequences designed to trick the model into making errors, revealing weaknesses in its handling of edge cases. The challenge is to balance between optimizing for high performance on training data and ensuring that the model can generalize well to unseen, real-world data. Overfitting and underfitting are two common issues that affect LLMs and their ability to generalize. Overfitting occurs when a model performs exceedingly well on training data but poorly on new, unseen data because it has memorized the specific details of the training examples rather than learning general patterns. On the other hand, underfitting happens when the model fails to capture the underlying patterns of the data, resulting in poor performance on both the training and test sets. Indicators of overfitting in LLMs include high accuracy on training data but poor performance on validation or test sets. To prevent overfitting, techniques such as regularization, early stopping, and dropout can be applied. The goal is to achieve a balance between bias, underfitting, and variance, overfitting, to ensure that the model can generalize well to new data. Few-shot and zero-shot learning are two paradigms where LLMs are expected to generalize from minimal examples or even zero examples, respectively, for a new task. Evaluating these scenarios is more complex than traditional supervised learning because the model is tasked with performing a task without much or any task-specific training data. Few-shot learning typically involves testing the model with only a handful of labeled examples, while zero-shot learning assumes that the model can handle tasks without any task-specific data. In these settings, metrics such as accuracy, precision, and recall are evaluated based on the model's ability to infer from instructions or examples. Improving performance in these scenarios often involves fine-tuning the model with a large, generalized pre-trained corpus, and using techniques like prompt engineering or auxiliary training tasks to guide the model's behavior. LLMs are often computationally expensive, requiring significant hardware resources to train and deploy. Evaluating LLMs in terms of computational efficiency involves assessing how much time, memory, and computational power is needed to run the model. While larger models tend to perform better, they come with high costs in terms of latency, energy consumption, and hardware requirements. Techniques like model pruning, quantization, and knowledge distillation can help reduce the size of a model without significantly sacrificing performance. These techniques remove redundant parameters, reduce precision, or transfer knowledge from larger models to smaller ones, enabling more efficient deployment on devices with limited resources. However, there is a trade-off between computational efficiency and model accuracy that must be carefully considered during optimization. Fine-tuning is a critical aspect of optimizing LLMs for specific tasks, as it allows models to adapt to domain-specific data and improve task performance. During fine-tuning, hyperparameters like learning rate, batch size, and the number of training epochs are adjusted to find the best settings. The learning rate controls how quickly the model updates its weights, while batch size affects the speed and stability of training. Hyperparameter optimization methods like grid search and random search systematically explore different hyperparameter combinations to find the optimal configuration. In practice, it's essential to monitor model performance on a validation set to avoid overfitting during fine-tuning. Additionally, more advanced techniques, such as Bayesian optimization or genetic algorithms, can be used to automate and optimize the search for the best hyperparameters. Evaluating LLMs in multilingual settings presents unique challenges, as models must perform well across various languages with potentially different syntactic, semantic, and cultural contexts. Metrics for evaluating multilingual models include cross-lingual performance on tasks like translation, summarization, and question answering. Standard metrics like BLEU and Rouge can be adapted for multilingual evaluation, but the model's ability to transfer knowledge from high-resource languages to low-resource languages is also an important consideration. Transfer learning and multilingual pre-training are commonly used to improve the performance of LLMs on multilingual tasks, allowing a single model to generalize across languages. One key area of research is improving the ability of LLMs to handle low-resource languages, where data scarcity makes training challenging. Techniques such as multilingual data augmentation, zero-shot transfer, and cross-lingual embeddings have shown promise in addressing these challenges. Bias and fairness are critical issues in the evaluation of LLMs, as models can perpetuate or even exacerbate harmful biases present in their training data. LLMs may exhibit biases related to gender, race, age, or socioeconomic status, often reflecting societal stereotypes. Identifying these biases typically involves testing the model on specific tasks or datasets designed to reveal biased behavior, such as detecting biased sentiment, word associations, or stereotypes in generated content. Metrics for evaluating fairness include demographic parity, equal opportunity, and disparate impact, which assess whether a model's predictions are equally fair across different demographic groups. Techniques for debiasing include adversarial training, counterfactual data augmentation, and bias correction layers that adjust the model's predictions to mitigate the impact of bias. Ensuring fairness in LLMs is not only a technical challenge but also an ethical responsibility to avoid reinforcing harmful societal biases. Text summarization tasks often use LLMs to generate summaries from longer text documents. Key evaluation metrics for summarization tasks include Rouge scores, recall-oriented understudy for gisting evaluation, which compare the overlap of n-grams between the model-generated summary and reference summaries. Rouge N, Rouge L, and Rouge SU are common variants that assess different types of summary quality, such as n-gram overlap and sentence-level similarity. Evaluating summarization can be particularly challenging when comparing abstractive summarization, where the model generates new content, versus extractive summarization, where the model selects sentences directly from the original text. Abstractive summarization often requires more sophisticated evaluation to assess the coherence, relevance, and fluency of the generated summaries, while extractive summarization focuses more on precision and recall in sentence selection. Despite these challenges, large-scale models like GPT and BART have achieved impressive results in both extractive and abstractive summarization tasks. Real-time performance is a critical consideration when deploying LLMs in applications such as chatbots, recommendation systems, or autonomous agents. Real-time inference refers to the ability of the model to generate predictions quickly enough to meet user expectations, typically within a few hundred milliseconds. Optimizing inference speed involves techniques such as batching, grouping multiple inputs together for simultaneous processing, and knowledge distillation, transferring knowledge from a large model to a smaller, faster model. Additionally, optimizing memory usage, reducing precision, quantization, and using specialized hardware like GPUs or TPUs can also significantly improve inference speed. However, there is always a trade-off between real-time performance and model accuracy. Speed optimizations may reduce the model's ability to generate highly accurate outputs. Tools like TensorFlow Lite, ONNX, and NVIDIA TensorRT are commonly used to measure and optimize inference latency for LLMs in production settings. Transfer learning allows LLMs to adapt to domain-specific tasks by fine-tuning a pre-trained model on a smaller, domain-specific dataset. The idea is to leverage the broad language knowledge that the model has learned from large-scale training data and adapt it to perform well on specific tasks, such as medical text classification, legal document analysis, or customer support dialogues. Performance evaluation on these domain-specific tasks is crucial to assess how well the fine-tuned model has transferred its knowledge. Common strategies include task-specific metrics, as well as domain-specific evaluation frameworks that assess whether the model produces useful, contextually appropriate outputs. Case studies have demonstrated the effectiveness of domain-specific fine-tuning in sectors like healthcare, e.g., clinical text mining, law, e.g., contract analysis, and e-commerce, e.g., personalized product recommendations, where LLMs are adapted to understand industry-specific jargon, regulations, and use cases. Regularization is a technique used to prevent overfitting during model training by discouraging the model from becoming too complex and capturing noise in the training data. In LLMs, regularization techniques such as L2 regularization, ridge regression, and dropout are commonly applied. L2 regularization adds a penalty term to the loss function that discourages large weights, while dropout randomly deactivates neurons during training, forcing the model to rely on different subsets of neurons each time it learns. Early stopping is another effective regularization technique, where training is halted when the model's performance on the validation set stops improving, thus preventing overfitting to the training data. Regularization helps improve the generalization ability of LLMs, ensuring that they perform well not only on the training data but also on unseen, real-world data. Interpretability and explainability are important aspects of evaluating LLMs, especially when these models are deployed in high-stakes applications like healthcare, finance, or law. Understanding how a model reaches its predictions can help build trust, improve model performance, and identify potential biases or errors. Several techniques are being developed to make LLMs more interpretable, such as using attention maps to visualize which parts of the input the model focuses on when making decisions. Saliency maps and layer-wise relevance propagation are also popular methods for explaining the internal workings of the model. However, the complexity and sheer scale of LLMs present significant challenges for interpretability. These models often operate as black boxes where even experts may struggle to understand their decision-making process. As the need for transparency in AI grows, ongoing research is focusing on improving the interpretability of LLMs. Training LLMs for low-resource languages presents significant challenges, as these languages typically lack large-scale labeled datasets or abundant textual resources. Evaluating performance in these languages requires careful consideration, as performance may be more sensitive to data scarcity and the quality of the training corpus. Strategies to overcome these challenges include leveraging synthetic data generated through translation, data augmentation, or back translation techniques. Transfer learning also plays a vital role in improving the performance of models for low-resource languages by pre-training on high-resource languages and then fine-tuning the model for the target language. Case studies have demonstrated that LLMs trained using transfer learning and data augmentation have achieved promising results in low-resource language tasks, such as sentiment analysis, machine translation, and named entity recognition, even in languages with limited data availability. Deploying LLMs in real-world production environments comes with several challenges, particularly related to optimizing the model for latency, memory usage, and scalability. LLMs are typically resource-intensive, and deployment environments such as cloud services or edge devices may have constraints on computational resources. Optimizing the model for latency involves reducing the time it takes for the model to generate predictions, which is critical in applications such as real-time chatbots or virtual assistants. Memory optimization ensures that the model can run efficiently without consuming excessive resources, which is essential for large models deployed at scale. Deployment strategies such as edge computing, where the model runs directly on the user's device, or cloud-based services that offer scalable infrastructure, can help manage these concerns. Tools like TensorFlow Serving, ONNX Runtime, and Amazon SageMaker are commonly used to monitor and manage models after they are deployed, ensuring that they continue to perform effectively in production environments. Dynamic quantization is a technique used to reduce the size and improve the inference speed of LLMs by reducing the precision of the model's weights. Quantization involves converting the model's weights and activations from higher precision, such as 32-bit floating point, to lower precision, e.g., 8-bit integer or 16-bit floating point, which reduces memory usage and accelerates computation. This technique can dramatically enhance the speed of inference without a significant loss in accuracy, particularly for tasks where a small degradation in precision is acceptable. Types of quantization include int8, 8-bit integer, and float16, 16-bit floating point, which strike a balance between performance and accuracy. Libraries such as TensorFlow Lite and PyTorch provide tools for implementing dynamic quantization, enabling efficient deployment of large models on edge devices and resource-constrained environments. Knowledge distillation is a technique used to improve the efficiency of large models by transferring knowledge from a larger, more complex model, the teacher, to a smaller, more lightweight model, the student. The student model is trained to mimic the outputs of the teacher model, thus capturing much of the teacher's performance in a more computationally efficient form. This technique allows for significant model size reduction and faster inference times without sacrificing much in terms of performance. Knowledge distillation is particularly useful in optimizing LLMs for applications with hardware constraints, such as mobile devices or edge computing environments. The teacher-student paradigm works by training the student to match the probability distributions or softmax outputs of the teacher, resulting in a model that retains most of the teacher's knowledge while being more efficient to deploy. Adapter layers are a form of efficient fine-tuning technique that allows LLMs to adapt to specific tasks without the need to retrain all the model parameters. Instead of modifying the entire model during fine-tuning, adapter layers add small, trainable layers within the pre-trained model. These layers are typically placed between the transformer layers of the model and allow the model to learn task-specific representations. By training only the adapter layers and leaving the rest of the model frozen, this approach significantly reduces the computational cost of fine-tuning and makes it possible to adapt large models to new tasks with minimal overhead. Adapters have been successfully applied in models such as BERT and GPT, where they provide an efficient way to customize large pre-trained models for a variety of downstream tasks without retraining the entire model from scratch. Evaluating long-text understanding in LLMs is more challenging than short-text tasks because models must manage longer sequences and retain relevant information over extended contexts. Common evaluation metrics for long-text comprehension tasks include document-level accuracy, reading comprehension scores, and coherence across long spans of text. The ability of LLMs to retain context over longer inputs can be influenced by the design of their attention mechanisms, as standard transformers often struggle with very long sequences due to quadratic complexity in the attention mechanism. Techniques such as sparse attention, memory-augmented networks, and hierarchical transformers have been developed to address the issue of long context handling, allowing models to capture information from longer text while maintaining efficient computation. These advancements have helped improve performance on tasks such as document classification, long-form question answering, and summarization of lengthy documents. Multimodal learning refers to models that are capable of processing and generating multiple types of data, such as text, images, and videos, in a unified framework. Evaluating LLMs in multimodal settings requires measuring not only the model's ability to understand and generate text, but also its ability to integrate and utilize other modalities, like visual or auditory inputs. Metrics for cross-modal tasks vary based on the specific use case. For instance, performance on image captioning tasks can be measured by combining image recognition metrics with text generation metrics like BLEU or Meteor. Similarly, for video-based tasks, models are evaluated for their ability to generate accurate and contextually appropriate descriptions. One of the key challenges in multimodal LLM evaluation is ensuring that the model effectively integrates information from different modalities, which can be difficult given the differences in data representations. Advances in multimodal architectures have made strides in improving LLM performance across these domains. Evaluating LLMs for dialogue systems requires assessing not only the accuracy of responses but also the quality of the conversation as a whole. Metrics such as relevance, informativeness, and engagement are crucial in dialogue tasks to ensure that responses are contextually appropriate and engaging for users. Additionally, it's important to evaluate the model's ability to handle conversational context, including maintaining coherence across turns and recognizing shifts in topics. Emotion and tone play significant roles in dialogue, especially in customer service, mental health, and virtual assistant applications, where the model's ability to adapt its responses based on sentiment is important. Case studies of real-world dialogue systems show how the evaluation must include both task-based metrics and conversational metrics. Evaluating LLMs for dialogue systems is a complex, multidimensional task that requires combining traditional metrics with subjective assessments of conversational quality. Text classification tasks, such as sentiment analysis, spam detection, and topic categorization, are central applications of LLMs. Evaluating LLMs on text classification involves measuring standard classification metrics like accuracy, precision, recall, and F1 score. However, in many real-world tasks, datasets are imbalanced, with certain categories being overrepresented. In these cases, optimizing for precision or recall may be necessary depending on the importance of false positives or false negatives. Techniques such as data augmentation, oversampling the minority class, or using cost-sensitive learning can help address class imbalance. Additionally, improving classification accuracy can involve fine-tuning models on domain-specific datasets, experimenting with different architectures like CNNs or transformers, and utilizing techniques like active learning to iteratively improve model performance. Hyperparameters are a critical component of LLM optimization, influencing how well a model learns from data and its final performance. Common hyperparameters in LLMs include the learning rate, which controls the size of the steps the model takes during training, the type of optimizer used, e.g., ATOM, SGD, batch size, which influences how much data the model processes at once, and the number of layers or attention heads. Tuning these hyperparameters can significantly impact the model's convergence speed and final performance. Methods for hyperparameter tuning include grid search, random search, and more advanced techniques like Bayesian optimization, which uses probabilistic models to explore the hyperparameter space more efficiently. Best practices for hyperparameter tuning involve using a validation set to evaluate performance during the search process, employing cross-validation for more robust estimates, and using early stopping to prevent overfitting. The learning rate is one of the most critical hyperparameters in training LLMs, as it determines how quickly the model updates its weights. A poorly chosen learning rate can lead to slow convergence, suboptimal performance, or even divergence of the model. Learning rate schedulers dynamically adjust the learning rate throughout training to optimize convergence and stability. Common scheduling techniques include step decay, reducing learning rate at fixed intervals, exponential decay, reducing the rate continuously, cosine annealing, smoothly reducing the rate and restarting periodically, and warm-up schedules, starting with a small learning rate before increasing. Dynamic adjustment prevents the model from overshooting optimal weights or getting stuck in poor local minima. Frameworks like PyTorch and TensorFlow offer built-in functions for implementing schedulers, such as reduce LR on plateau in PyTorch and exponential decay in TensorFlow, helping practitioners efficiently optimize their LLM training process. Standard transformers struggle with quadratic time complexity in self-attention, making them inefficient for very large inputs. To address this, researchers have developed alternative architectures that optimize speed while maintaining accuracy. Sparse transformers reduce the number of attention computations by only attending to a subset of tokens, making them ideal for long context applications like text generation. Linformers approximate self-attention with linear complexity, significantly reducing memory and computation needs. Other approaches include reformer, which uses locality-sensitive hashing to reduce attention overhead, and performer, which leverages kernel methods to approximate attention. Each of these methods balances trade-offs between speed, memory efficiency, and accuracy, making it essential to choose the best-suited approach based on the application's constraints. Large language models often suffer from high inference latency, making them less suitable for real-time applications. One major cause of latency is the computational overhead of processing long sequences with dense layers of self-attention. To mitigate this, model pruning removes redundant or less significant weights, reducing computation without sacrificing too much accuracy. Knowledge distillation, as discussed earlier, helps create lightweight versions of models that can deliver similar performance with lower latency. Additionally, optimized serving frameworks like ONNX Runtime and NVIDIA TensorRT provide accelerated inference through techniques like operator fusion, quantization, and hardware-specific optimizations. Efficient batching strategies and asynchronous processing further enhance inference speed, making LLMs more deployable in latency-sensitive environments. Fine-tuning large models on specific tasks is often expensive, requiring substantial GPU resources. Parameter-efficient fine-tuning (PEFT) methods provide an alternative by adjusting only a small subset of model parameters while keeping most of the pre-trained weights frozen. LoRA, low-rank adaptation, introduces trainable low-rank matrices into the transformer layers, drastically reducing the number of parameters modified during fine-tuning. Prompt tuning modifies the input prompt embeddings while keeping the model weights unchanged, whereas adapter tuning inserts small trainable modules within transformer layers. These approaches allow organizations to customize LLMs efficiently without retraining the entire model, making them cost-effective and practical for real-world deployment. Hyperparameters are a critical component of LLM optimization, influencing how well a model learns from data and its final performance. Common hyperparameters in LLMs include the learning rate, which controls the size of the steps the model takes during training, the type of optimizer used, e.g., Atom, SGD, batch size, which influences how much data the model processes at once, and the number of layers or attention heads. Tuning these hyperparameters can significantly impact the model's convergence speed and final performance. Methods for hyperparameter tuning include grid search, random search, and more advanced techniques like Bayesian optimization, which uses probabilistic models to explore the hyperparameter space more efficiently. Best practices for hyperparameter tuning involve using a validation set to evaluate performance during the search process, employing cross-validation for more robust estimates, and using early stopping to prevent overfitting. Fine-tuning and pre-training serve different purposes in LLM development. Pre-training involves training a model from scratch on large-scale corpora using self-supervised learning, requiring massive computational resources and extensive data collection. This is necessary when developing a new foundational model or when existing models are insufficient for a domain. Fine-tuning, on the other hand, adapts an already pre-trained model to specific tasks using smaller datasets. This is ideal for applications like domain adaptation, e.g., medical text processing, or task-specific customization, e.g., chatbot response generation. Fine-tuning is far more computationally efficient than pre-training, as it requires modifying only a fraction of the model's parameters. Companies and researchers must weigh the costs and benefits. While pre-training provides more flexibility, fine-tuning allows for practical, cost-effective deployment of LLMs with strong task-specific performance. Transfer learning allows LLMs to leverage pre-trained knowledge and adapt it to new tasks, significantly reducing the need for large-scale labeled data. By taking a general-purpose language model and fine-tuning it on specific domains, e.g., finance, law, or medicine, models can achieve high accuracy with relatively little training. The benefits include faster convergence, reduced computational costs, and better generalization, especially in scenarios where collecting task-specific data is challenging. However, knowledge transfer is not always seamless. Issues such as catastrophic forgetting, where the model loses general knowledge while learning a new task, and domain shifts, where vocabulary and linguistic patterns differ between pre-training and fine-tuning datasets, must be addressed. Domain-adapted LLMs like BioBERT for biomedical texts and FinBERT for financial data demonstrate the effectiveness of transfer learning in specialized applications. Bias in language models refers to systematic unfairness in predictions, often caused by imbalances in training data or reinforcement of stereotypes. Bias can emerge from various sources, such as historical biases in training data, unrepresentative datasets, and inherent model architecture limitations. Detecting bias requires specialized evaluation methods, such as demographic disparity analysis, counterfactual fairness testing, and word embedding association tests, e.g., WEAT. Strategies for mitigating bias include data augmentation with diverse examples, adversarial training to counteract bias, and debiasing techniques such as equalized odds adjustments. It is crucial for developers to implement continuous fairness evaluations to ensure LLMs produce ethical and unbiased outputs, particularly in high-stakes applications like hiring, law enforcement, and finance. Explainability in LLMs is critical for trust, transparency, and regulatory compliance. Unlike traditional machine learning models, deep transformer-based architectures are black box models, making their decision-making processes difficult to interpret. Common challenges include hidden dependencies in attention mechanisms and complexity in token embeddings. To improve explainability, researchers use techniques like attention heat maps, which visualize how the model distributes focus across input tokens, and SHAP, Shapley additive explanations, which helps understand feature importance. Other approaches, such as counterfactual explanations, show how small input changes alter model outputs, providing insights into decision boundaries. Explainability is particularly important in regulated sectors like healthcare and finance, where stakeholders require interpretable AI to ensure compliance and accountability. Training large language models is prone to several issues that can impact performance. Vanishing and exploding gradients occur when backpropagation updates become too small or too large, disrupting learning stability. Solutions include gradient clipping, using better activation functions like ReLU, and proper weight initialization. Overfitting happens when a model memorizes training data instead of generalizing. Techniques such as dropout regularization, data augmentation, and early stopping help prevent this. Conversely, underfitting indicates that the model is too simple to capture data complexity, requiring architectural improvements or longer training schedules. Debugging tools such as TensorBoard, weights and AMP, biases, and Hugging Face's Trainer API allow researchers to visualize model performance and detect anomalies early in training. Deploying LLMs in real-world applications requires balancing model size and performance. Model compression techniques help reduce computational costs and memory footprint while maintaining acceptable accuracy. Quantization converts high-precision weights to lower-precision formats, e.g., FP32 to INT8, reducing memory usage. Pruning removes redundant weights, shrinking model size while retaining key information. Distillation, as discussed earlier, transfers knowledge from a large teacher model to a smaller student model. Each technique has trade-offs. Quantization improves speed but may reduce accuracy. Pruning requires careful tuning to avoid degradation, and distillation simplifies the model but needs high-quality teacher outputs. Model compression is essential for mobile applications, real-time inference, and AI at the edge, enabling deployment in resource-constrained environments. Reinforcement learning with human feedback, RLHF, is a technique used to align LLMs with human preferences by optimizing model outputs based on explicit human feedback. RLHF involves 3 key steps: 1. Collecting human preference data, 2. Training a reward model to score responses, and 3. Fine-tuning the LLM using reinforcement learning, typically proximal policy optimization, PPO. The advantage of RLHF is that it enables models to generate safer, more coherent, and more human-like responses. However, challenges include subjectivity in feedback, scalability of human evaluations, and potential biases in reward models. A notable case study is OpenAI's ChatGPT, which leverages RLHF to refine conversational quality and prevent harmful outputs. RLHF has become a powerful approach for improving LLM reliability and safety in real-world applications. Deploying LLMs at scale raises several safety concerns, including misinformation generation, toxic content, and security vulnerabilities. To mitigate these risks, developers implement content moderation filters, reinforcement learning constraints, and human-in-the-loop review systems. Addressing hallucinations when LLMs generate plausible but false information requires improved fact-checking mechanisms, retrieval-augmented generation (RAG), and confidence estimation models. As AI models become more autonomous, future challenges in AI safety will involve ensuring transparency, reducing bias, and preventing misuse. Ethical AI deployment requires a multidisciplinary approach that combines technical solutions with regulatory oversight. Security is a major concern in deploying LLMs, as they can be vulnerable to prompt injection attacks, where adversarially crafted inputs manipulate the model into producing unintended or harmful outputs. Another risk is model inversion, where attackers infer sensitive training data by probing the model with queries. Additionally, LLM jailbreaking refers to bypassing safety filters using cleverly phrased prompts to extract restricted information. To enhance security, developers must implement input sanitization, adversarial training, and strict access controls. Rate limiting and user authentication help prevent abuse, while continuous monitoring allows for identifying emerging threats. Ensuring secure deployment requires multi-layered defenses and responsible AI governance frameworks. LLMs sometimes produce hallucinations, where outputs seem plausible but are factually incorrect. This happens because models predict text based on statistical patterns rather than true understanding. Hallucinations pose a risk in applications like legal and medical AI, where accuracy is critical. Strategies to reduce hallucinations include fact-checking models, confidence estimation, and post-processing filters. One effective approach is retrieval-augmented generation (RAG), which integrates external knowledge bases to ensure factual correctness. Benchmarking with human evaluators and automated metrics also helps measure hallucination rates. While hallucinations cannot be entirely eliminated, careful model design and continuous fine-tuning minimize their impact. To assess LLM performance systematically, researchers use standardized benchmarks that evaluate capabilities like reasoning, comprehension, and factual accuracy. Popular benchmarks include GLUE for general NLP tasks, MMLU for multitask language understanding, and HELM, holistic evaluation of language models. However, comparing models is challenging due to differences in dataset biases, prompt design, and fine-tuning strategies. Emerging evaluation frameworks focus on holistic and multifaceted assessments, considering robustness, efficiency, and fairness. Organizations like OpenAI, Hugging Face, and Stanford are developing transparent benchmarking platforms to ensure reliable model comparisons. Traditional LLM evaluation relies on static benchmarks, but real-world performance requires adaptive evaluation techniques. One method is active learning, where models continuously learn from user interactions to refine predictions. User feedback serves as a key metric, allowing real-time adjustment of model responses based on preferences. Automated monitoring tools, such as Hugging Face's Evaluate Library and OpenAI's Moderation API, help track LLM performance across different tasks. Self-supervised evaluation techniques also leverage LLMs themselves to assess response quality, enhancing scalability. A combination of human feedback loops and automated assessments ensures continuous performance improvement. Many LLMs perform well in English but struggle with low-resource languages due to limited training data and linguistic complexity. To address this, researchers use data augmentation techniques such as backtranslation, parallel corpora generation, and subword tokenization to enhance learning. Transfer learning leverages high-resource language models, e.g., English-trained models, to improve performance on related languages, e.g., Hindi, Swahili. Cross-lingual adaptation with techniques like multilingual embeddings enables better generalization across languages. Promoting linguistic inclusivity in AI requires collaborative data collection efforts and fine-tuning LLMs for diverse linguistic contexts. Recent advancements in AI involve multimodal models that combine text, image, and audio understanding, e.g., GPT-4v, Gemini, and Flamingo. Training multimodal LLMs is challenging due to data alignment issues, higher computational requirements, and complex fusion architectures. Techniques like contrastive learning, e.g., CLIP, and cross-attention mechanisms help bridge modalities efficiently. Applications include AI-powered virtual assistants, medical diagnostics, and creative content generation. Optimizing inference for multimodal tasks requires efficient embedding techniques, pre-training with diverse datasets, and hardware acceleration, e.g., TensorRT for GPU inference. LLMs are not just autonomous tools, they work best when combined with human expertise. Human-AI collaboration allows users to fine-tune models dynamically, providing interactive feedback loops to refine responses. In AI-assisted coding, e.g., GitHub Copilot, CodeLlama, LLMs help programmers debug and optimize code. Similarly, LLM-assisted scientific research accelerates discovery by summarizing literature and suggesting hypotheses. The future of hybrid AI-human workflows includes copilot systems, where AI augments human decision-making rather than replacing it, leading to safer, more transparent, and controllable AI models. As LLMs evolve, self-improving architectures are being explored, where models continuously refine themselves based on feedback. Scalability challenges persist, as models beyond trillion-parameter scales require breakthroughs in hardware efficiency, e.g., neuromorphic computing, sparsity techniques. Another emerging trend is the integration of symbolic reasoning, logic-based AI, with neural networks to enhance problem-solving. However, ethical challenges grow as models become more autonomous, requiring stricter governance, accountability frameworks, and AI safety measures. The future of AI lies in balancing capability improvements with responsible deployment, ensuring that AI serves humanity effectively. Memory management is one of the most significant bottlenecks in LLM training and inference. Large models, such as GPT-4 and Palm, require hundreds of gigabytes of VRAM, making optimization essential. Gradient checkpointing reduces memory use by recomputing activations as needed instead of storing them. Mixed precision training, FP16/BF16, halves memory consumption with minimal accuracy loss. Zero redundancy optimizer shards model parameters, gradients, and optimizer states across GPUs, minimizing redundancy. Additionally, offloading techniques, such as deep speed offload and FSDP, fully sharded data parallel, move computations to CPU or NVMe storage when GPU memory is limited. Hardware accelerators, including NVIDIA H100, Google TPUs, and AMD MI300, provide efficient memory handling, enabling large-scale LLMs to run on feasible infrastructure. Efficient memory management directly translates to lower costs, higher throughput, and greater scalability, making it a priority in AI model deployment. For real-time applications like voice assistants, chatbots, and autonomous agents, reducing inference latency is crucial. Several factors impact inference speed, including model size, computational complexity, and memory bandwidth. Model quantization, e.g., INT8 precision, reduces computational cost while maintaining accuracy. Efficient batching improves throughput by grouping requests but must be balanced to avoid excessive delays. Caching mechanisms store frequently accessed information, reducing redundant computations. A more advanced technique, speculative decoding, predicts multiple tokens in parallel and verifies them afterward, accelerating response generation. Hardware optimizations also play a role. Tensor cores in GPUs, TPUs, and custom AI accelerators, e.g., Cerebras, GraphCore, maximize efficiency. Ensuring low latency while maintaining response quality is a challenge, but is essential for deploying interactive AI at scale. LLM training is highly energy-intensive, consuming thousands of kilowatt-hours per training run. As models scale beyond trillions of parameters, sustainability concerns grow. One approach to mitigating energy use is mixture of experts, MO, where only a subset of parameters is activated for each input, significantly reducing computations. AI companies are also investing in green data centers, utilizing solar, wind, and hydroelectric energy to power their AI workloads. Federated learning allows decentralized training, distributing tasks across multiple edge devices instead of relying on a centralized, power-hungry data center. Optimized training algorithms such as Lion, evolved sign momentum, and Eta factor further cut power consumption by reducing redundant calculations. As LLM adoption grows, balancing performance with environmental sustainability will remain a major challenge for AI researchers and industry leaders. Fine-tuning large LLMs is computationally expensive, requiring significant GPU resources and storage. Low-rank adaptation, LoRA, provides an efficient alternative by adding trainable low-rank matrices to specific layers rather than updating the entire model. This drastically reduces the number of trainable parameters by up to 99% in some cases, allowing rapid adaptation with minimal hardware requirements. LoRA also enables storage efficiency, as only the adapter layers need to be saved rather than an entire fine-tuned model. This makes it ideal for scenarios requiring multiple customized models, such as chatbots, industry-specific LLMs, and personalized recommendation engines. Since LoRA keeps the original pre-trained model frozen, multiple fine-tuned adapters can be easily swapped, enabling dynamic deployment of specialized AI applications. The next generation of AI models will continuously learn and evolve instead of being static. Continual learning enables models to update without forgetting previous knowledge, addressing the issue of catastrophic forgetting. Automated evolution techniques, such as AutoML and Neural Architecture Search (NAS), will allow models to optimize their own structures dynamically. Memory-augmented transformers will integrate external storage to retain long-term contextual knowledge, improving personalization and adaptability. However, challenges remain. Ensuring stability, security, and bias mitigation is crucial as models autonomously update. As AI systems move towards self-improvement, regulatory and ethical considerations will become increasingly important in governing AI evolution and decision-making. Reinforcement learning from human feedback, RLHF, is a technique for optimizing LLMs by aligning their responses with human preferences. Instead of purely relying on likelihood-based training, RLHF introduces a reward model trained on human-labeled comparisons of different model outputs. The training pipeline involves 3 stages. 1. Pre-training the base LLM, 2. Training a reward model based on human feedback, and 3. Fine-tuning the LLM using proximal policy optimization, PPO, to maximize the reward. RLHF has been successfully used in GPT-4, Claude, and ChatGPT, improving coherence, ethical alignment, and response quality. However, challenges include reward hacking, where models exploit loopholes in reward functions, and scalability issues in obtaining high-quality human feedback. Future optimizations in automated preference modeling and scalable reinforcement learning will further enhance the adaptability of RLHF-driven LLMs. As LLMs scale, dense computation becomes a bottleneck due to memory constraints and energy inefficiency. Sparse computation addresses this by activating only relevant parts of the network per input, significantly reducing overhead. One common technique is mixture of experts, MO, where only a few specialized submodels, experts, are active for a given query. Sparse transformers, such as the Big Bird model, improve attention efficiency by using localized and global attention mechanisms, avoiding quadratic complexity. Sparsity reduces compute demands but introduces complexity in routing, load balancing, and hardware optimization. Ongoing research in adaptive sparsity and hardware-accelerated sparse kernels will determine the viability of large-scale sparse LLMs. Transfer learning allows LLMs pre-trained on large, general datasets to adapt efficiently to specific domains. Pre-trained models, such as GPT-4 and Llama, learn universal linguistic patterns, enabling cross-domain generalization. Fine-tuning adjusts model weights for domain-specific data, enhancing accuracy but requiring significant compute. Prompt engineering, on the other hand, steers the model's output without altering weights, making it a low-cost adaptation method. However, challenges remain. Fine-tuned models can become overfitted to niche data, reducing generalization, while prompt-based approaches may lack deep adaptation. Hybrid strategies combining parameter-efficient tuning, LoRA, adapters, with advanced prompting are becoming the preferred approach for scalable, adaptable AI solutions. LLM evaluation relies on standardized benchmarks to measure performance, generalization, and robustness. Key metrics include perplexity, lower is better, accuracy on tasks, e.g., MMLU, GLUE, and BLEU/Rouge scores for text generation quality. Benchmarks like HelloSwag, Common Sense Reasoning, GSM-8K, Math, and Big Bench, Broad Tasks, provide comprehensive assessments. Robustness testing involves adversarial examples, stress testing on long inputs, and hallucination detection. However, benchmark scores do not always reflect real-world usability, necessitating continuous human evaluation and real-world deployment testing to ensure reliable performance in dynamic environments. Hallucinations occur when LLMs generate false or misleading information, a critical issue in high-stakes applications like medicine and law. Detecting hallucinations involves confidence scoring, adversarial probing, and fact-checking against knowledge bases. Retrieval augmented generation, RAG, mitigates hallucinations by grounding responses in external, verifiable data sources, reducing over-reliance on internal parametric memory. Additionally, self-consistency methods, where multiple model outputs are compared to filter out inconsistencies, improve factual accuracy. Future research in neurosymbolic AI and verifiable reasoning models aims to create LLMs with higher factual reliability and reduced hallucination risks. AI alignment ensures that LLMs adhere to human values, fairness, and safety guidelines. However, defining universal ethics is challenging due to cultural variations, biases in training data, and evolving societal norms. Debiasing techniques include dataset filtering, adversarial training, and reinforcement learning from ethical preferences. Guardrails such as constitutional AI, used in Claude, and harm reduction frameworks, like OpenAI's moderation tools, help control model behavior. Despite these efforts, challenges remain in detecting subtle biases, preventing misuse, and ensuring transparency. Future advancements in AI oversight, regulatory compliance, and participatory ethics will shape responsible AI development. Deploying LLMs on resource-constrained devices requires model compression to reduce computational load while maintaining accuracy. Quantization lowers precision, e.g., FP16int8, to reduce memory usage, while pruning removes redundant weights, shrinking model size. Knowledge distillation trains a smaller student model using a larger teacher model, preserving essential knowledge while optimizing efficiency. These techniques enable LLM deployment on mobile devices, embedded systems, and IoT. However, compression often results in accuracy loss and reduced expressiveness, requiring careful optimization to balance efficiency with performance. LLM optimization is evolving toward automated, adaptive, and explainable evaluations. Hybrid evaluation combines human oversight with AI-driven assessment tools to improve alignment. Self-improving AI architectures, incorporating meta-learning and continual self-adaptation, promise enhanced efficiency and robustness. Regulatory considerations, including transparency, data privacy, and bias mitigation, will increasingly influence LLM deployment in commercial and governmental applications. The future of LLM evaluation will focus on balancing scalability, interpretability, and reliability, ensuring models serve human-centered objectives efficiently. This lecture covered evaluation and optimization techniques for LLMs, including memory efficiency, inference acceleration, sustainability, RLHF, sparsity, hallucination mitigation, and ethical alignment. Despite rapid advancements, challenges like robustness, interpretability, and ethical concerns remain unsolved. Future breakthroughs in self-learning AI, neurosymbolic reasoning, and efficient scaling techniques will shape the next generation of LLMs. Advancing AI requires collaboration across machine learning, linguistics, cognitive science, and policymaking, ensuring responsible and beneficial AI development. Thanks for watching. For more courses and interview materials, please visit our website at bowz8.com.